Welcome back. Morning we saw brief introduction about optical diagnostics, right? So why do we use optical diagnostics? So because they are non-intrusive, right? Non-intrusive means they won't, in theory, they don't interfere with the whatever the process happening, right? So otherwise, if you put a probe, then that will alter the flow. Let's say you want to measure the temperature in somewhere like a flame. The moment you put a thermocouple, obviously that will absorb heat and that will alter the flow. So that is the reason then you use optical diagnostics. But again, professor was telling, right? So the advantage is good, like it is not interfering with that. But the what is the drawback of it? You need to have access to it, right? Let's say if you want to see internally what is going on inside the engine or the combustor, right? You need to have optical access to it. That means you need to see what is going on. So now if you go back and look at, does it really non-intrusive? Up to some extent, but not like, okay, if you want to see, you have to replace the metal parts with something like a transparent to the light. So that will have a different properties. And then let's say if I have to see through the curved portion, there will be a distortions. You need to correct for those distortions. Or you need to make, instead of a curved surface, I need to make a flat surface. That will change the flow. To an extent, yeah, it is. But and also in the morning you saw like everything involves lasers, right? Sensitive cameras. Sometimes the signal you get will be really small one. So you need to intensify the signal, right? So with all this, yeah, it gives like really the good information and highly like with the time temporal as well as a spatial. So let's say if there is a flow you have, if you want to measure anything, so then you use a hot wire anemometer, then you need to move at different distances, like spatial resolution you get, so will be limited, right? So you can't move almost like every point, so you need to move a certain distance, right? Otherwise it takes a lot of time. And time, with the time variation, it depends on, like we all studied in heat transfer, a response time of a thermocouple, right? So you calculate based on lumped heat analysis, we calculate what is the response time of a thermocouple. If you put, by the time it reaches 99% of the flow condition, there will be a time. So you will not get with the time result. So it will take some time for it to respond and give the actual reading. So that you call as a temporal. So the spatial and temporal accuracy of the physical based measurements will be little slower. So whereas in lasers we get, or optical diagnostics, not only the lasers, optical diagnostic doesn't mean that you always have to use lasers. So you can use any laser, like you capture the photons, it could be even LEDs we see in a moment. So now morning professor talked about some of the techniques used for combustion, all that. I'll just discuss briefly about the sprays and little bit details on the particle image velocimetry, where, so which is a commonly used technique to measure the flow field velocity. So we'll discuss that today. And afternoon, as I said, like there's a small change in the schedule. So afternoon we look at this. One of the simplest technique is backlit imaging. So then, but using that you can get a lot of information. And most of the studies, so the simple like a spray, all that, that will be like a really good tool. So we'll look at into that in the afternoon. And tomorrow, whatever the session we have, we'll try to do some PIV experiments or take the images, or just we'll show the seeding how that happens and then take some images and process it. So right. So as I said, I'm going to, so little bit of, again, it is not an exhaustive measurement techniques. I'm not going to discuss, just a glimpse of ray diagnostics, and then some of the things we did. So that also will be showing like that. Like why do we need? If you look at the principle of atomization, right? So where do we use this phrase, right? Yesterday we were talking about, now you might have been wondering like high speed flows, jet engines, and where is this spray, right? So thing is, In combustors, wherever you use a liquid fuel, right, you have to take, like in the tank, you have bulk fluid. So then you have to put it into the combustor. You just can't dump entirely. So first you need to break into small drop. So right. So this process where you take a big drop or big chunk of a liquid and break into very small drops, that is called the atomization process. So the way the bulk liquid is transformed into a simple drops. So this transformation is usually through a first what do you need to do? Take this liquid and make it into the sheet, thin liquid sheet, or into the jet. So that jet first breaks into, like later in the images we can see, first that sheet or a jet breaks into big drops, which we call it as, if there are drops spherical, we call it as a drop. If it is non-spherical, still somehow look like a drop, we call as non-spherical drop. It doesn't even look like a drop, like a big threads, we call it as ligaments. So those are the trees. If it is just like long stretched one, so you don't call this as a drop. How does this process happens? So it is just because of the aerodynamic action. So right. So if you take here, so if your liquid sheets, this is the classical image where you can see that sheet turning into the breaking into the drops. So usually, like you might have seen, right, water taps. Like if you just open a little, what happens? It will just come like a simple jet. And if you keep increasing the velocity, it will start breaking up. What is happening? So there is a, if you look at this, the relative velocity goes up between the air and the liquid, so these aerodynamic forces causes some disturbances. They keep growing. They break the sheet, or here in this case a jet, into like a big drops, right? Or sometimes this is just due to the aerodynamic action, but sometimes there will be, even you can use the centrifugal forces also to just you, if you have like a spinning disc, if you put a liquid on a spinning disc, what happens? It will form like a sheet that will break into. So, or sometimes there are use electrostatic forces like ultrasonic atomizers. Your nebulizers sometimes use these ultrasonic atomizers. There will be a small vibrating plate, and that will create tiny these drops. Now again, this process, earlier we call it as atomization. Then what do you call, what is a spray? Collection of these drops moving in a particular fashion. You don't call something like all, there are drops if they are moving in all directions. So we never call it as a spray, we call it as sort of a mist. Mist is good. Like you see in day-to-day life, if something is just fine drops going all around, we call it as a mist, we never call it as a spray. Spray has some particular direction to it. All this collectively, they move one direction. And so what is the best example you can see as a spray, as a written here? Naturally you observe, like rain always moves down, so it is a collection of, it is like a spraying of liquid. Or if you just go to like ocean shores, the waves, there will be like all this small mist coming up. And then this also I told, like a droplet, you call it as more or less spherical shape. It need not be exactly spherical. Then why do we use sprays and where do we use, right? In general, like anyway, so one is the engines, definitely, like fuel. First of all, why do we need to break this liquid into small drops? What is the reason? And why do we need to increase the, what is the, why do we need to increase the surface area? Better? See, all, first of all, all these combustion processes, we like initially we stick to combustion process. In this combustion process, first you need to mix air and fuel, right? To mix, both has to be in the same form. Like if it is a liquid, this has to be in a liquid. If it is a vapor, the air is in gaseous form. You need to make this as a vapor, then only you can mix. Once you mix, then only, like if you mix properly, then combustion will be proper. Otherwise you will end up, if it is a improper mixing, you end up having a lot of problems, right, in engines. Like so you can have first of all, if initially itself it doesn't mix properly, you may not be able to ignite at all, so you'll have unburnt fuel going in. Or otherwise, if we are able to mix and have zones where there is a very lean and where is a rich mixture, so lean part the flame will travel slowly, then you will have suddenly quenching can happen because it is not strong enough to sustain the flame. Whereas in a rich part, so then you will end up having a lot of soot kind of thing, or unburnt, partially burnt, you end up having a lot of carbon monoxide, this kind of a fuel. So you need to mix them properly, right? So if you, how do you make? First you need to vaporize, and to vaporize, so all this heat and mass transfer process is, where does it happen? On the surface. It doesn't happen internally, it is on the surface. So first liquid drop has to evaporate, this vapor has to go out. See what happens if it is a stagnant and evaporate, so this vapor will just stay there, right, and it reaches a saturation. Once it reaches saturation point, then it will not no longer, so this mass has to diffuse, right, and for this, and you all know, for any liquid to evaporate, what heat it requires? Latent heat of vaporization. So latent heat of vaporization, it has to get, then only liquid becomes vapor. For that heat, there has to be some heat transfer from the surrounding to the drop, right? That also happens through the surface. So both. So now if you increase the surface area, so then, so this will accelerate. So how do we increase the surface area? Just like simply take, like if you have a initially 1 centimeter drop to break, so how many 1 millimeter drops you can make? Yeah, 10. No, so volume is same. So 1 mean volume, you have to equate the volume, not the like a diameter, right? So the volume of 1 centimeter drop, and just like imagine that is like a huge drop. You will never have very rarely you will have 1 centimeter drop. Take 1 centimeter drop. This volume only, which one you will conserve? Volume only, right? Total volume. I make into 1 millimeter drop. So 10 cube. So you can make 1000 1 millimeter drop if I have 1 centimeter drop. So then calculate the surface area change now, right? It will be a 100 times higher, right? R square it goes, right? So, or yeah, you can calculate. So the surface area will, the change in the surface area will be large. That's why you try to make as small drops as possible so that it will evaporate quickly, right? So it is not only the evaporation, the fuel problems. Some places where you have a gas absorption, there also you need to have large surface area, right? So, or even a coating, all that. So you take the same liquid, I spread over the large surface, it is better, right? Even in agriculture space. So you take same volume and spread it over the large surface. So you need to make into fine drops. Again, then you may ask saying that, can I make really fine drops? Let's say few micron. Is it always good? That is also, there is a problem with that also. It depends on the application. You can't make like a really small drop. So there are problems like it will not have enough momentum. If you make really small drops, the momentum will be really small because the mass will be small. They lose the momentum quickly. They will not be able to penetrate. Just like again combustion. So if you take a cylinder or a gas turbine, usually the injectors are at the surface or at the center, one point, or at max a ring kind of thing, right? And then this has to go and spread across the chamber. So they need to have some momentum also to go, right? So to penetrate through that. If you make too fine drops, they will not have a momentum. Again, in a case of agriculture or even in the gas absorption, if you spray some liquid and there is a spray tower, this has to travel all along to keep going and collect at the bottom and use. If it doesn't have enough momentum, this will just go out. Or agriculture spray, you just spraying it, you would have seen some videos. If there is a wind, then all the drops will go. So both are important. Size is important and as well as the momentum. So these are these things. Why do we use sprays? Where can you find sprays? I think probably everywhere in day to day life, right from your perfumes, everyday morning deodorant, it is a form of a spray. So natural sprays, so you would be seeing like many places, right? So right from rain, the automobiles and gas turbine combustors, like wherever they use liquid sprays. So not only the combustors, nowadays you use urea injection into the exhaust systems to reduce the NOx. Again, there also there will be a liquid solution spray into the exhaust, so that then agriculture application need not tell, all the pesticides and nutrients delivery to the leaves are done through that. The biomedical devices, quite a few biomedical devices, right from that, like if you have a sprain, that or the inhalers also, they disperse some medicines, so they make into like a tiny form of these drops, and that goes in. And fire suppressant equipment, you would have seen that they'll use firefighters, they right, even the water also just like in a jet form, so they use spray into that, or even a dispersant, some fire safety equipment, if you just open it will come like a foam or a. And food processing industry is one of the big industry which uses all your chocolates coating, or the milk powders, boost, malt, all these are, so quite a few of them are done by spray drying again. So there also, you look at heat and mass transfer, like you have to spray it and dry, you have to take out the all moisture out, so to store it for long. And quite a few other industrial applications also, right from the chemical processing, all these industries also, they do use sprays. And then you can ask like what kind of a characteristics you're interested in sprays, right? So first thing is, we take a nozzle upstream, we are interested in what is the pressure. So the pressure and the flow rates, liquid, how the flow rates are upstream of the nozzle or the spray pressure. And then once it comes out, and how far it is, cone angle is nothing but how we, in a moment we see in the images, how far it is spreading. So what are the boundaries of the spray and the angle made in this, between these boundaries, so that you can calculate like how long it spreads. Then this tip penetration is especially useful for the case where you have a transient, right, engine kind of thing. You open the valve, and with the time, how far they travel. So that is called a tip penetration. And then how much mass is injected per se. So that is also important. If you have a transient, if it is a continuous spray, what is the flow rate we are interested. If it is a transient kind of a diesel or the fuel injector kind of a sprays, so what is the amount of mass injected per. And then once we look, this is sort of a macroscopic. Microscopic is just you look, zoom, sort of a microscopic is just zoom into small portion and see, and what are the size of the drops, and you don't get, you hard or nearly impossible to get all same size drops in a spray. So there will be a distribution of means you have, this is the minimum drop, this is the maximum drop size, in between you will have a different distribution. There are different ways to represent these distributions, right? And then the velocities, not only the size but also that, depending on the, again depending on the pressure, how fast these drops are traveling. So that is also drop size distribution, right? So now we generate a sprays, and then we are interested in this, and what kind of methods we use to characterize. We are interested in these characteristics. How do we measure? Simple way is, I think people earlier used to use this. I collect all this, whatever I spray, collect in a small chamber, measure it, or so that I divide this zone into different. I just put a lot of cups and then collect it, and I can even get the distribution of it. So right, so collection of, if it is a drying kind of application, so they just collect the particles, look under microscope. Or earlier people used to use, like before the laser diagnostics, or that people used to use, have any kind of a spray, freeze it, You create a very low temperature, freeze it, collect those solid drops, measure under the microscope, and you get the size distribution. Or still, some of the applications they use what you call as a bromide paper. So I put this, so when the drop hits, it will create an impact sort of a pattern. Take this paper and or look under a microscope and get all the information. What is the size distribution? Of course, there the assumption is this will just hit. There are some difficulties. Or people do use X-ray imaging also to look into that. So laser diffraction, the morning professor told, right? So any light interacting with the medium, so there will be a diffraction based measurements are there. And shadow imaging, we saw that. Today we will also have a look at some of the shadow imaging. And there are some interferometric methods, which interferometric method means you create a pattern by interfering, like, right, if the light waves of different, if there is a phase difference, if they interfere, you get an interference pattern like a dark and bright fringes. Use that. Yeah, fringe pattern. So use that fringe pattern to do measurements. There are different measurement techniques. And laser induced PLIF is nothing but planar laser induced fluorescence, scattering. The morning we saw, right? If the the light wavelength you use is smaller than the size of the particles, so you get a scattering. And most of the sprays, that is what we have. So the size will be of the order of microns. The visible light wavelength, usually the green or red they are used, they are of the order of 500, 600 nanometer range. So it will be always like from sprays you have this kind of. So there are other advanced method, structured laser illumination, which is structured laser illumination for planar imaging, which is called as SLIPI. So that is used kind of a dense spray. So all these optical methods you have to see through the sprays, right? But if it is too dense, what happens? Like you have some drop here, some drop here. I'm looking from here. Now you see that there are two distinct drops. Now let's say if I have like this, for you it looks like this is one oblong shape, and like that if there are multiple drops, it looks like, okay, there is a complete sheet kind of thing. So they use this structured illumination to get that, or get a multiple scattering. And or the time of flight is again depending on the obstructions you cause, light reaching the sensor will be different. Like let's say if I have here multiple drops, usually like when you have a sprays at the core, you have a lot of drops. Like if it is a cone, right? Let's say if it is a cone, at the center of the cone, so you have the path, or what you call as the optical path, is larger. At the edges it is smaller. Likewise, if there is a density, a lot of dense drops, the optical path will be larger. So right, then the light ray traveling at this point will reach slightly later compared to the light ray traveling at. And there are methods use. This is called a ballistic imaging. Briefly I'll tell about it. They use that. So and if you are a sprays, then what can be, I think we just are like starting with what happens to the nozzle. We can measure the internal characteristics, mass flow rates. I'll just show some of that. So I just took some examples what we did. First of all, we are interested in whenever you have a nozzle, first you need to know what is the size of orifice, all that, right? Basic structure of nozzles. So this was one injector which used in port fuel in automobile applications. If you look at the sizes, so they are of the order of 200, that kind of a few hundred microns. So right, so probably, yeah, it's the evening or so, we have this nozzles. You can look at around. I think some of the students, they looked around. You can clearly make the difference between port fuel injector, where the injection pressures are very small. You inject into the port of. So diesel injectors, they use really high pressures of the order 1500, 2000 bar. Some of them may go up to 3000 bar. the size of the orifice will be really small, obviously, right? So if I want to inject the same amount of a quantity, if I keep the pressure difference large, the injection velocity will be large. So then if my mass flow rate is constant, m dot will be equal to rho density, because all the liquids are incompressible or nearly incompressible, we will not have much change in the density, into area times velocity. So if I increase the velocity, I have to reduce the area. So you need to use small orifices, so small that they will be of the order of 50 micron. With the naked eye, it will be difficult to distinguish them. So that's the reason, like low pressure injectors, you will have slightly, again it depends on the mass flow so you want. And just an example, like same kind of injector, there are two holes, the size is 270 micron. If the increase the number of holes, then they reduce the size. So this is like a 4-hole injectors, you have like a really small. So then we say that, okay, once we measure this, then we need to see what is the, how the spray looks like. You have, whether you have a series of drops or there are any, all this, still there is a liquid, because you want by the time this interacts with the air, you want as much spherical drops as possible, right? Again, sphere gives you have large surface area to volume ratio. Like, so this is the simple spray structure. You can do again using simple, this is simple backlighting. Simple backlighting is nothing but, like, I have a light source. If I keep this thing and put a heat here, so wherever there is a hand, like it will create, you might have seen I think you can do all these things. You put a light and then put your hand, it will create a shadow. The only thing is, if you put a spray, afternoon we will see it will create a shadow there. So, and if it is sparse enough, you can clearly see. Or if you capture, again importance of like how long you open the sensor, all that is important. If something is moving really fast, right, and if you expose the sensor for large duration, what happens? It will look like a tree. So you need to have, yeah, just to tell like what is a so there will be a called motion blur. You would have seen, like just in a cameras, when you take a photo, if somebody moves during this exposure, what happens? You'll not be like, there will be a blurring, right? Especially happens at like a sports, all that thing, if something is moving fast. So you need to close the shutter, or you have to allow the light sharp enough that within that time frame, this has not moved, or the object has not moved large enough, right? So that it will get like you will not see the any blurring motion. But that, so then what happens? Now again, that depends on the velocity. If something is moving slow, you are okay. So right, if something like really going slow, it is fine. But if you have a high velocity thing, then illumination also has to be so fast, or your camera exposure has to be so fast that you almost like a time freezing in a time. So then the problem is, again, like a photography, you would have seen that if you allow, let's say there is a all, like there will be a shutter before the camera, it just opens and closes in a short time. So the moment you open and closes for a short time, amount of light it allows will be less. So you would have seen that if you reduce the exposure time, what happens? The image, will it get brighter or darker? Right? You open, you're closing, or you're opening for very short duration. The amount of light goes is very small. You get really dark images. So that means the brightness of the light outside has to be really. So just an example, like when you take the night mode photos, so click it. How long you have to hold? You have to hold it for longer duration or shorter duration? You have to hold for little time and then without shaking your hands, so that during that exposed time there is enough light reaches the sensor. So just like that. So if you want to capture something moving really fast, the light has to be sufficiently large enough. That's why, like, you're using any kind of high speed flows, you use like really bright lights. So, or the lasers are usually the lasers are nanosecond. The laser duration is very like few nanoseconds. That's why you get like really sharp images, because light is bright light for very short duration. Even say the one more thing with the lasers is, now you are not controlled by the two things here. Just yeah, two things here. So one thing is, I can open camera shutter for long, have a light very sharp, right? When there is no light, it will be dark. Just like imagine that here we switch off all the lights and put a camera, nothing will be visible. Suddenly somebody flashes on light on you, so it will be visible for that duration. So camera can be opened whole duration. I can have light only for a small duration. That is one thing, right? Or other way is, I'll put a continuous light, open camera for very short duration. That also is possible. Both ways possible to freeze the motion, right? One, I just have a flash, or I'll open a camera for shorter duration. So these lasers will do the second one, where the camera can open for long, but this laser will be for nanosecond. So then you can imagine that the velocities, even very high velocities, you can still get the sharp images. So here the images, here the images are taken like, so this is back illuminated image. This is just a scattering image, me scattering. You pass a light through this, right? Spray. So these are the instantaneous images, but instantaneous images will keep varying. So over the average time, we get from these images, we get a spray structure. Okay, this is the boundary. So there are some drops here, so all the sides, and in between it is not broken up. Still there is a liquid. So all that information you get. Now, once you have this information, now if you want to see what is the size of these drops, that means you need to zoom into this area. So for that, so you use kind of a, like this is the structure. So you use this kind of images. So where, so you use a specific type of lenses, so which is called long distance micros. Now one thing, so usually with the imaging, right, you would have seen that macro images. When you take any flowers, insects images, what do you have to go really close, right? So really close. The working distance, what we call, is a really small. But the problem with this, if something is spray or hot temperature is there, you can't go really close, right? So you have a problem. So imagine that in the spray, you have to capture few microns. Other day you're telling about 50 micron drop. So you have to have enough resolution to capture that. You need to go really close. The working distance, what you call, from the lens surface to the imaging plane. So that will be really close. Sometimes or most of the times you can't go that close due to many things. Could be like, if it just hits, the spray hits, there will be still some fluctuations. Because of it hits, it can damage the instrument. So there is a special device called long distance microscope, so which is widely used to focus into very small area from a safer distance. I would say that 50 centimeters to 1 meter distance, you can still focus onto the area of few centimeters, few millimeters. So right, so that kind of thing. And then this laser, so you put laser, and this laser you convert into the, this is called a diffusers. So means this laser usually comes in a beam form that is spread onto a small disc, right? And then there are other methods, like otherwise if you just use a laser, it will create what you call as a speckles. Then they use something like a, what you call as a diffuser, right? So probably like in a SLR camera, if you have some light like this, if you try to take the image of light, what you see that individual LEDs. But if you put a white paper on that, you get really smooth. That is diffusing light. So that kind of these are the few images. So once you do that, so you can get this kind of a image. So which is, let's say if you look at it, this is in microns. This is 2 millimeter by 2 millimeter area. You are taking this, so you are imaging a 2 millimeter by 2 millimeter very small area. So if you use image this area, now you can calibrate this. So afternoon we will see how do we calibrate also. So right, so it's like a calibration is simple. I'm viewing this area, how much length it is. That's it, right? How much distance it is. And how many pixels, because all the camera sensor will have few pixels. So if this is 1000 pixels, say imagine that this 1000, 2000. So let's say 1000 pixels is here, let's say 2 centimeters, 2 millimeters. So each pixel will be 2 micrometers, right? So now I can, like, no need to, there are, you can use MATLAB algorithms, if not the commercial softwares. So you can use MATLAB algorithms, you can eliminate, you find that what is the total pixel area of this, let's say this drop, right? So what is the total pixel area? From that, so we can get the size of the drop. Again, imagine that all this case, we are thinking that the drop is, even if it is a slightly non-spherical, we are equating the area and getting it. And if this drop is distorted in the other direction, we will not get that information. So that you have to keep in mind. This is like a planar measurement, only in this plane. And all this, whatever the optics you have, will have a what you call as a depth of focus. Means within a short zone, it will be focused. You move away from that zone, it will be blurred. So even front, it will be blurred. So you have to be aware of that. What is the depth of focus? Usually, if you smaller the field of view, smaller the depth of focus. So right, that's what happens if you see image like a cap. If you take the wide angle lens, everything will be in focus. The moment you zoom into very small area, so background will be defocused, right? So that is also one thing. Like unlike your eyes, probably the eyes have infinite depth of focus. Everything you can be focused. So, but in optics, that is not possible. Now you have this image. So right. So now I can take two images consecutively, right? So from this you get a size. So right, I can get a size by calculating the area of each shadow. We call it as this is a shadow created by the drop. I can get the area. Now if we take one more image after some t, so right, what happens? This drop here is t, after delta t, its position will be moved, right? So its position is slightly moved. Now I can correlate these two and get, this is frame 1, this is frame 2. In this time, it moved by this distance or this many pixels or this much distance. By delta t, I can get the velocity, right? So that is how. So this is called, if you measure the size, it is called PDIA. So particle / droplet image analysis. So you are analyzing the image and getting the size. So that is called PDIA or shadow imaging. Or then if you use a second frame, you can get the velocities also. That is called particle tracking velocimeter. In the other presentation, I'll just briefly discuss about the difference between PIV and PTV. So this is like you get the size as well as the velocity. So this is the simplest technique. So you don't, the only thing is, and what is the time difference between the two frames I take, right? So all that, and what is the size I have to have, field of view I have to have, that depends on the, say let's say if my pixel resolution is 10 micron per pixel, I can't measure 10 micron drop, right? Because it is a 1 pixel, there will be a noise, right? So at least you need to have a drop should have like a 4 to 5 pixel, then you can rely. That means if my resolution is 10 micron, I can rely everything above, let's say 50 micron drops, something like that, or 30 micron drop. You can't. So, or inversely, you can think of, like, I have to measure 10 micron drops, all the spray. So that means your resolution has to be 2 micron. That means you have to go really close or have really good camera which has like, yeah, which has like a really large sensor, right? So one thing is, these SLR cameras you have 24 megapixels. So you have almost like 5000 by 5, means 5000 pixels by 5000. But the thing is, they can't go to very really low shutter speeds. So that's where you can't freeze the motion. If something is moving slowly, yeah, that is the best. If some slow movement thing, no need to have a hi-fi like high speed imaging systems, lasers, simple lab setup. You can just use a DSLR camera. People do use that DSLR camera, and then just a small LED light, you can do it. So there are other slightly different methods which I'll be. So usually it depends on the application, ma'am. So like most of the heat and mass transfer application, we call it as solder mean diameter. So which is sigma of all volumes of a drops by sigma of all surface. So that is application. If some application like I want to have a spread something, so this is a volume mean like a 50% diameter, or the simply number mean diameter. What is that? Depending on the application, depends on. And then how there is a what we call as a span factor, relative span factor. So which gives how wide the distribution is compared to the mean. So right. So there is a different methods are there, or we call it as dV10 is a volume per 50% of dV50 is 50% of the volume lies in sizes below. So usually you have all that numbers. So it depends on the application. For quite a few of applications wherein heat and mass transfer is there, it is a surface to volume ratio. For those cases, it is called solder mean diameter, which is a ratio of total volume of the drop. See, because each sizes will be there, we write sigma of all volumes by surface. So there is another method which is called eyelids or IMI. There is a different name. So interferometric laser image from drop size, or interferometric me imaging. So all this. So interferometric particle image, these are all one and the same. What happens here is when the light falls on the drop, so you have two things. There will be a reflection, direct reflection. So right, there will be a direct reflection from the surface, right? Another one is light goes, hits the drop and bends, and then comes, there is a refraction. So one, if you take two rays, one is reflected ray, one is refracted ray. And now if you look at the travel time, the refracted ray will have some time delay because of there will be a phase difference. If you try to interfere them, like for them, so you will create this kind of a fringes. At a focal point, they focus, this beam will focus at one point, this beam will focus at other point. At a focal plane, they look like two separate dots. One drop, so one from the reflected rays, you will have one focal point. From refracted, you will have one focal at the focal point dot. But out of, when you just focus your camera slightly before or after, you have what you call as this. They both will interfere and form fringes. The something like this fringe pattern away from the focal point. So here at the focal point, you have this, right? Two dots, it appears like a two dots. But away from the focal plane, so these both will interfere and form these fringes. If you can count this number of fringes you get, so there is a me theory, so you have a formula that is inversely proportional to the diameter. So right, you can get the details, like, so it is inversely. So that means if I can count the number of fringes, right? So if you can count the number of fringes, I can deduce the droplet diameter. Now you can ask, do I have to do it manually? No, there are image processing methods. So image processing methods, you can identify the area and count the number of fringes, and from that you can get the size of the drop. So for that you need to know the refractive index of the particle. So if you look at, this is an individual drop, it is really easy. If there is an individual drop, I know like fringe came from that drop, I can. Then if you go to the sprays, it becomes chaotic. So you have all kind of, are you able to see clearly? Like, so you see that there are multiple drops overlapping. That's all that you can. So that means if it is really dense, so we're not going to. And there are methods that they use what is as a condenser. Like instead of circle, I make this. They put a small slit kind of thing. So there are methods to compress or use optics to compress this circle into thin line, right? So there are methods. to do that, and up to some extent that works. Again, if you compress this circle into line, and if there are two overlapping lines, then there will be a problem. So again, all these cases you don't want to have very dense space. So there are no methods till now to work on really dense space except that ballistic image. So, and other slightly variation or most popular method is called phase Doppler anemometry, right? Phase Doppler anemometry or PDPA. Anemometry is finally measure the velocity. Like hardware anemometry is used to measure the velocity, right? Similarly, like phase Doppler anemometry is to get the velocity. It is just now, earlier the fringe pattern was formed by the drop. Now you create a fringe pattern purposefully by intersecting the two laser off slightly off phase laser beam. So then what happens? Now you allow the drop to travel through that. So now whenever it passes through the bright spot, so it gives the signal. Like you create a small pattern here, right? Whenever there is a drop travels through this, you get this kind of a signal, bright and dark, right? So based on that signal intensity, so you can get the size, right? How long it takes to completely go through. If the size, I have a small point here, right? If the drop size is large, it will start getting the signal here, and till it goes completely, I get the signal. Based on that, you can get the size. And then based on when the peak occurs, if you have a multiple this thing, based on when the peak occurs, you can get even the velocity. You have two, this slightly advanced version is called PDPA, particle phase Doppler particle analyzer. So where they use a multiple, what you call as a receivers. So right, and observe that when this peak occurs between these two, from there you can even get the velocity. There is a slight deviation for that. So that is one thing, and it is used again here also. You see that this is quite a expensive one. So then again, the non-dense space will not work. So if you look at the first case, we focus into the small area of the prey and image it. So right, the thing is you can even get the non-spherical drops. So even if it is whatever the shape it is, you will get in the image. But here to IMI and PDPA, we assume that the drops are spherical and even not transparent to the light, right? So they have to be transparent to the light. So that also, otherwise, like whereas the shadow imaging, even the particles you can get it. So there are other even advanced method. I was telling that, right? So where based on the path or travel time of the light, so they measure. This is called a ballistic imaging. So like, so you impinge a light on this imaging, and in principle, just like to a glimpse of it, I think you can even get a lot of information. It is just measures that, okay, if there is a light, right, coming through this, how long it takes to get. So there will be, they use what you call as a femtosecond laser, nano and femtosecond laser or femtosecond optics to capture the time delay at different levels, and from that I reconstruct algorithm to use algorithms to reconstruct. So what is the density at different places of the spray? So from that you can get, again, you get the, like here there is a liquid core. So this is usually the sprays will have a lot of drops and liquid core. So wherever there is a liquid core, the photons will arrive really late, right? Liquid will, in the liquid, speed of light is like it will travel less, so the obviously, or it will obstacles are there, so that will come light. So same way, like this is, so again same thing, like, so ballistic photons are the ones which goes through, and then they remove all the other photons and get it. And there is other, you can get a lot of information on that, but this requires, this is based on, ballistic image is based on, as I said, on the travel time. And there is other method called structured illumination, because what happens is, generally if you pass the laser sheet, get the scattering image, there will be a multiple scattering coming up, because one scatter light from this there is a spray, I illuminate in this axis, then what happens? Whatever the scattered light coming from here will hit the drop here. So there will be multiple scattering. So to avoid that, they use this structured illumination where you change the phase of the incoming light, or take, there will be a methods to use what you call as a gratings, put it and pass this light to different paths to get it, and then image it, and then reconstruct everything. So that is one method. So again, as I said, these are the few methods, and if you, there are quite a few methods. I think some of them I am going to give it in little applications. So now I talk about few applications of a diagnostic of spray. So this is again a simple backlight imaging. So right, you can get correlate. This is sort of effervescent spray. So where you can clearly see that when there is a dense spray, even the background gets dark, kind of thing. So there will be a lot of, so from these kind of images I can get the structure, whether it is the liquid is breaking up or not, or it is just like a core, or there are a lot of ligaments, or I can even get a process this image. I can subtract the background, you take the image and then get just a sharp boundary, I get the cone angle, or even look very close and see what is happening. This is some sort of a backlit imaging to see how the breakup is happening, or you see that PDIA to get the sizes. And this was, we try to see internally what happens inside the nozzle. So to make that, you need to make the nozzle transparent, make it acrylic. The problem here is, so here this is the internal ones. So and then there is a refractive index, matching of refractive index. The liquid refractive index was almost close to the acrylic refractive index. So then what happens? Inside the nozzle, so this is effervescent injection. Just to give a brief, I think just jumped into effervescent. So effervescent injection, you inject a small amount of gas into the injector so that it forms bubbles, just like your Coke. When you put it in a glass, you see that lot of bubbles coming. Or some of the tablet, they call it as effervescent tablets. Just you put it in a water, all this kind of a tablets, they create a bubbles, right? So that is called, a process is called effervescence. So you put a small bubbles, or the gas bubbles, or any gas inside the liquid, so that this you are putting at a high pressure, and then the moment they see the pressure difference, what happens? Gas will try to expand and break the liquid. So you can get at low pressures, because gas at high pressure contains much higher energy because of the compressibility, so it breaks up. So now what happens? You have this two-phase flow, we call it as so inside the nozzle, what happens? Because of the refractive index matching, liquid, what you see liquid is a transparent, and gas is dark one, because gas refractive index is lower. So, and the moment it comes out, you are in the medium like a gas, right? So gas looks transparent, liquid looks dark. So that is, there is a flip. If you do see this kind of experiment, the way you interpret also will be. So then some of these kind of a things, we look at the patterns, how the breakup happens, all that. Maybe I'll show some of the videos. And then I was talking about the transient sprays, right? So this was a continuous. You just switch on the injector and continuously you see. And if it is a, so then a transient, so you open the injector and then see how it evolves. And this is called a penetration. This is time equal t equal to 0 with time, how long it travels, that is the penetration. Sometimes you can use multiple techniques. Like one of the thing we used was multiple techniques to get some information. So morning professor said about planar laser induced fluorescence. So fluorescence, you all know, right? It absorbs light and emit. So again, there is a small difference between the inelastic scattering and the fluorescence. So right, so both cases, inelastic scattering is absorbed. It will not absorb the light continuously. That means completely. So the fluorescence case, the light wave is absorbed completely and then go to the high energy state and comes down. So that's the reason, yeah, it comes down. So then you will get a different wavelength. So here we use this phrase. So now the fluorescence is a volume phenomena, right? So it absorbs light, absorbs completely in the liquid, right? And then there is a signal, and scattering happens through the surface. So right, one is a volumetric phenomena, one is a surface phenomena. So one is proportional to the volume. The signal, fluorescence signal, is proportional to volume. Then surface, the scattering signal is proportional to the surface area. If I take the fluorescence signal, ratio of fluorescence signal to the volume surface signal, it will be proportional to the diameter. Just now, earlier you said, right, total volume, sigma of all volume to the surface will give a shorter mean diameter. So now if I take the signal ratio, that will be proportional to the shorter mean diameter of the spray. So now, so earlier, like if you remember, we have to zoom into very small area to get the sizes. Now now I can pass a laser sheet and get the size information for entire plane, isn't it? So, but there is a catch here. You would not get, so we said that proportional, but what is the proportionality constant? That for that you need to calibrate at multiple places. For that you need again either zoom into small area and get the size information, or use a method kind of a PDPA to get that. So that is one. Again, this is the oil. So maybe I'll just quickly, again, so this is diesel sprays, and if you use oils, you can see the how the breakup changes. Maybe I'll just touch upon the other simple backlight illumination for this droplet explosion kind of thing. So what Professor, we did during the postdoc with Professor Lionel. So initially started with, like, I take a diesel. We'll demonstrate some of this thing. The simple thing is, like, if you have a cooking oil and water, what happens? Sometimes if there is a water in the oil, splash, it will just like explode. Why it explodes? Water boiling point is lower than the oil, right? So the moment temperature reaches 100, all the water will evaporate, then volume will increase largely, then it will splash. So same thing we can use for the fuels to our advantage. So right, so what we call as a micro explosion, you mix low volatile, or high volatile means very low boiling point liquids into conventional fuels or high viscosity fuels, then put it, so they'll create this explosion. So this was a simple setup. So again, just the idea was to see that except the high speed camera, there was nothing, no costly item. So like a tiny toy igniter, put a drop on a small thermocouple, ignite it. So even like a continuous, so you can see here, like if it is a smooth burn, you don't see any undulations, and here there is an undulation, so that means some jets are coming. Here this case, you see that suddenly something happens and it disappears, right? Yeah, something just disappears from there. So if you, this is just, if you look at this, this is just a luminosity. So you're not capturing any light. There's other natural luminosity of the flame, right? Whatever the light coming from the flame. Now, if I want to see what really happening close, so you need to see what is going on here. For that, if I really have to see that, first I need to record at high speed, and then I have to illuminate such a way that it will overpower the flame. Otherwise, if the flame is there, that will block what is happening. So you need to have an intensity such a way that, so you don't want to see the flame, you want to see inside what is happening. So right, you use like really high Okay, I'm not sure this, okay, at least next video will show like here. So we put like a really strong backlight and then would capture this explosion. So this is called you still see some sort of a haze here, right? So then you can see that some small drops coming and they getting explode. And if you further observe, if you further closely observe, so first this big drop breaks into small, small will break, and if you closely observe the ones which are small, again this also you can also demonstrate that, and even in the background there will be tiny blips. So right, so this demonstrate like if you want to, this initial droplet is of the order of millimeter, then these are of the order of one order of magnitude, 100 microns are there. The one further breaks up will be order of few microns, which we are not able to capture with that resolution. If you want to capture that, you need to further zoom in, right? That is one thing. And then again, so what if these are the fuels? So look at what happens in engine. Like this was, we had a small high pressure chamber. So the diesel spray and put at a high temperature, it will get ignite. And from this also, like this kind of experiments also, so you can get, if you want to compare between the fuels, you can get like what is the flame spread, how long it takes for the complete combustion. If you use different type of fuels, completing the combustion may take little different. From that you can get that kind of information. So like at any point you can get what is the total flame area, right? It all depends on that. Or you can even zoom in and get some other information on like very close to nozzle. So what happens? This. So the other simple technique used is this is called, I think I'll just here. So there is a train of drops going into, this is called a secondary. The one bulk liquid breaking is called primary atomization. Once this drops also, they travel at very fast, because if the drop travels at very fast, then they can further undergo into like a into very small fragmentation till you have that aerodynamic forces are not sufficient to break this, create any disturbances. Till then it can break. So this is some other process, secondary atomization process. So these are the few techniques. All these cases, if you look, I think quite a few of them are just simple backlight imaging. Put a light, from that you can get a lot of information. So this is about some techniques. Again, as I said, this is not the exhaustive one. There are quite a few other methods used in sprays. But things to remember is when you are dealing with it, you have to know the limitations of the technique. So, right. So as I said, all this light interacting assumes that as a PDPA or PDIA, IMI, they assume that drops are spherical. And then otherwise, if they are non-spherical, then either they reject it, right? The signal will be, they reject the signal. It is fine if there are one or two non-spherical this thing, right? But if there are, like you are measuring very close to the atomizer where there are a lot of non-spherical drops, then you end up with a problem. Like out of 1000, you reject 900 and measure 100. So that will not give the correct representation. And the other thing is, if they are too dense, then also will be a problem. So that's why the measurements usually made sufficiently far that, so there is vertical laser, they are not optically dense. So that is a term used. So this is about the spray diagnostics. Probably I'll just to give a quick thing about the particle image velocimetry, especially. I think quite a few of these topics I already covered. Yeah, I'll quickly go through this. Again, we saw that the flow measurements. So there are different ways to measure the flow. So one is flow measurement. We all do the flow measurements, right, using a mass flow meters, all that. So then optical method or the other, sometimes either you can measure the flow directly, flow rate, or in a test section I can measure the velocity, right? if you can measure the velocity and into area, you can get the flow rate also. So like a conventional methods we can use, just like flow meters, hot wire anemometer, all that. So but again, as I said, so these are all the quantitative methods, but they have what we call as a temporal resolution, or spatial resolutions will be really small. I think it is the same. So and then the temporal resolution may be like, especially temporal resolution is important if you have very unsteady flow. So let's say you use a hot wire and there is a flow going on. It will take an average after some time. So if you have any fluctuation with the time variations, especially turbulent flows, you will not be able to capture. You get the mean velocities. You will not get the variation in the velocities. And again, a spatial also. Again, spatial resolution, what we say, the moment you put a probe, so that will affect that. So that's why you have some methods, optical methods. So hot wire is conventional measurement, and then the point measurement, again it is an intrusive one. Then there are methods called laser Doppler velocimetry, so or the particle image velocity. These are the two methods you use. So right, so then laser Doppler velocimetry is exactly like I was telling, like PDA. So phase Doppler anemometry, anemometer is to measure, so that is also called laser Doppler velocimetry or laser Doppler anemometry. So it is like using a laser, you create a fringe, and then at that point you are measuring the velocity, right? At that point you are measuring the velocity. So whereas the PIV is a planar measurement. In a single shot I can get in an entire plane. So that is the main difference. Again, use the lasers, but no need to create a fringe pattern. So like that. So these are all like, these are optical techniques. And the main problem here, if you look at, so just flow, like if there is a air flow, you will not get any scattering, right? Air molecules are really small, you will not get any scattering. So you need to, what you call as a seed the flow. So seeding the flow means something trace which gives the scattering signal has to be there. So you illuminate it, it should get the signal, right? It should scatter. So right, later we see that when you use this, when you seed that particle, you have to take care again. These particles should follow the flow. It should not go like whichever direction they want. So that means, first of all, these particles should be buoyant. That means there won't be, like if you leave it in any flow, there should not be a net force kind of thing. And then only that it should be a Stokes flow kind of thing. They should not induce any flow condition. So that means they should follow the flow very smoothly. So that's why choosing these particles will be really important. Just like you would have seen that smoke is the easiest way to trace, right? If there are, you would have seen that all these incense sticks, agarbatis, just they'll go and mix. If there is any undulations, it will just simply mix it. Smoke particles are so small that it will do. And in water, again, you can use slightly denser particles, some solid particles. So, and then these velocity measurements. So any phenomena, you will have three components of velocity, right? So three components of velocity, and plane also, spatial coverage. So there are two things, like number of components. C is for components, D directions. I have at the different directions, I have all the three components. So the different, like laser Doppler velocimetry is zero dimensional. That means in a zero dimensional means at a point it measures. So right, one dimensional, you measure in a line all the components, in a plane all the components, in a volume all the components. So that's how you can. So mostly like laser Doppler velocimetry, based on that it is a point measurement, but you can get three components provided you have enough receivers, right? So PIV is, like the particle image measure, you are illuminating the plane. So if you are illuminating the plane, so you get a measurement in the entire plane, that is two dimensional. And what else you can get? You can get actual component of the velocity. Let's say if this is a plane, two components, you can't get the third dimension. If you have to get the third component, in a two-dimensional plane, that is called a stereo PIV. Means it's like eyes vision, like we can get the three-dimensional this picture, right? So stereo vision is that you put two cameras and try to get image from one side, how much it moved second, so you can get the third component of velocity. If you do all 3D in a volume, get all 3D component, that is tomographic PIV, which requires 4 cameras. So it is like the cost will go up. In a normal PIV, you need 1. So a stereo you need 2, tomographic you need 4, right? So then again, image processing algorithms. So PTV, I think again this thing I explained in the previous case also. So you have two snapshots separated by time. So right, so there's a particle tracking velocimetry. So this is what I showed, like there also, and then from that I think same image showed other time also. So we get this velocity. Now in the particle, we call it as particle tracking velocimetry. Why? Because you are individually seeing these particles. That means the density is so sparse that I am individually tracking the particles. But if I have to take a large, so that means then I have to zoom into very small. Imagine that just now we told that if you want to measure the velocity, this particles has to follow the flow, right? That means it should be small enough. If it is heavy, then what happens? They will just settle down with the gravity. So it will not follow the flow. You will have a net component, it will go. So that means you have to make it so small that it will just will follow. It will not, except the drag force, there should not be any net force on that. And if you make it small, if you track individual particle, the resolution has to be really small. That means your area, it becomes, again you are going towards the point measurement, right? Then what is the advantage of then rather than that we use a PIV. So particle image velocimeter, you don't track individual particles, so you track the patterns. So we will come to that. So if you take the PIV setup, what it requires is a light sheet, camera, and then some calibration source, and you need time. This calibration source is like you need to calibrate what is the distance, right? So that, and then timing, because you need to time these pulses of the lasers, right? You need to know the time between two images, that is for the timing unit. And then after that, processing, like once you use algorithms to process. So why light sheets? Why can't I just keep imaging, right? Illuminate using volume. So why? Because if I illuminate in a plane, that is fine. Like close it and pass the laser sheet, I just illuminate only in the plane. Whatever is there in the plane, I get it. Otherwise, if you get rather than sheet, if I illuminate entire area and image it, then what happens is just like your cameras. Like if you have a camera, you would have seen that depending on the focal length, like different, the relative sizes so will change. So depending on the focal length, relative sizes will. Now if I image entire thing based on what lens I use, the relative thing between the different planes, let's say I illuminate this plane, that plane, and the third plane, and if I use 18 mm lens, that looks like displacement looks very small, whereas this displacement looks very large. But if I use other lens, so that's the reason you illuminate in a single plane and don't image any other thing, right? So again, tomographic PIV, they use multiple cameras to get that aspect. That so then a CCD camera. CCD camera is nothing but it is like a photodiode. You have multiple photodiodes. So what happens? The light falls on that. That is converted into charge. CCD is nothing but charge coupled device. So all the photon intensity is converted into the voltage. All that is mapped, and it will show like populate the image. And then so there are two ways you can do this PIV measurements. So one is so double shutter cameras. So these can take 2 frames in a short time. So I have a continuous illumination, I take 2 images in a short time. So Usually these cameras you can set the first frame exposure and second so all like you need this double shutter camera, otherwise if you use a single image so you can't use, or use a high speed camera, you get a sequence of images and take two image as a pair. You need image eventually you need image pair to correlate, right? You can't have a velocity from a single image, so that is a thing. And also you need to illuminate this too, so that means the light source, the lasers also has to have two pulses. So that is the, so and then so we need to have distinguishable pairs, we will come to that again. This is PTV kind of so now this seeding, so you need to create this if you need to seed the flow such a way that so it should have something like this. So if it is too sparse, right, if the seeding particles are not filled entire area, then you can see individual particles moving, so that goes closer to PTV. And if they are not sufficient, you can still distinguish between the individual, okay, sorry, pointer, if it is dense but still you can see individual particles up separately, that is also, there is a method that is called, you don't call as a, the technique is same but it's called laser sheet velocimetry. It is same, it is like a scattering signal by correlate. And if you the seeding is sufficient enough, you don't, there you don't see the individual particles, you see only the patterns in the PIV. So that is a PA. So then what happens is, then you take two frames and then create what you call as a autocorrelation or a cross correlation. That means intensity in the first images, you map the intensities, like I take a small area in the image, right? So that is called the interrogation window. Let's say I have 50 pixel by 50 pixel. So I take 5 pixel by 5 pixel block and try to see this intensity where it matches, right? So you can do that, right? So this I have intensities, then where it matches I keep on checking, like it is, if you look at it, okay, where is this mapping, where, so okay, here the pattern of this drop is matching the pattern here, that means this block of particles moved this much distance, right? So you're not tracking individual particles, but so what is the advantage? So you need not resolve each and every particle, so you can have a group of particles, that means I can have a much larger area, right? And they use like a double exposure camera, so that is called a, so uh, there are, as I was telling, like you can take two frames, separate frames, and then correlate, that is called a cross correlation. There is a earlier method was like you need you're not having this earlier there were no what is it, the precise control over the timing. What they used to do is, especially with the cameras, you expose large enough, just now I was telling that you expose camera large but light you put only for very short duration, so right, so then it will get illuminated, camera will be still open, then I again put a laser once again, means in the same frame I'll have two instances recorded, right? So then I can look, then the problem is what happens, let's say in a frame I am here, in the same frame I appear two places, right? I know how much distance I moved and I know the between that time, like I'm here, like you're taking the image, so right, it is exposed twice, you put a flashlight on you, so one time you are here, one time you're here, so you know the time difference between the flashlights and you know the distance. I can measure the velocity but I don't know which direction you moved, right? You don't have, is it like I know the distance but which is the first position, which is the second position, you will not have idea if it is same frame, right? So whereas the other case is where you know, like first light source is what you call as a double pulsed twice, and you have a camera two frames, you know that first frame refer to this time, second frame refer to this time, so then you can do what you call as a cross correlation. So like these are the some, this interrogation window will try to find cross correlation functions, then they come up with the cross correlation functions. They use like fast Fourier transforms to get that. So there's a big like a theory behind these algorithms. Then autocorrelation is nothing but I is the image. In each image, they multiply the intensities at a given point to the other image at other given same image at different location. So if you look at I, both are I, like the same image they are comparing. Here it is different image I and I star. So these are the things. There are a lot of these commercial softwares. There are commercial softwares, but there are quite a few good open source softwares. So that OpenPIV, MATPIV is a MATLAB based ones. Then OpenPIV, PIV lab also there are MATLAB codes, and some of them has a very good GUIs, all of them. So no need to even go to the coding part. So yeah, this is a like if you have this two images, you do FFT and get the correlation functions. So all that. So these things you can go through, and then general limitation is again this also you need not have complete like if the exposure is long, instead of seeing the particles you see a lot of hazy stuff. So maybe we can just demonstrate that also. If you use a SLR camera, if the flow is very fast, you just see like a smoke going. If you can't distinguish particle pairs, it will be difficult to. And then time between the pulses. Let's say some flow is going. So right, this is the frame I have, flow is going, and the one pulse comes when this pair is here, and the second pulse has to come, or the second image you have to take with when this is within the frame, right, or only a small distance. If it goes out of the frame, then there is no way. So that you need to have a little bit of idea on what is the velocities you are expecting. Based on that, you need to have this idea. So there is a theory behind like what is the resolution. Again, it depends on the magnification and the velocities, like maximum velocity you are expecting, all that you can calculate. But the whole thing is there's a spatial range and dynamic velocity range. Means what is the velocity you can measure, kind of velocities you can measure, and what resolution you can do. So these two are there, right? So you can't have both. So that is the whole thing. So this ratio or the product of this is generally a constant. That means if I have to resolve the velocities, I have to compromise on the spatial resolution. If I get a spatial resolution, I have to compromise on the velocities. Just like, or it is easy to imagine in a PTV kind of thing, right? If I want to capture the small particles, then I have to focus into small area. If I focus into small area, then even if I have a slight larger velocities, these particles move out of the plane within no time. So both of them you can't have. The same thing is valid. So right, and seeding, again I think this also I measured. So seeding particles is very important. So that determines whether you are measuring the actual velocity or the apparent velocity. So right, if you seed the particles correctly, then you can measure which follows smoothly, so you get the actual velocity. Otherwise the velocities will be different. So again, the gravitational it has to be a Stokes flow, it's neutrally buoyant. Then there are equations to see the response of that. So in general, like generally the particle requirement is it should be small enough to follow the flow. And I also, if it is too small, then we go to remember Mie scattering. If they are too small, what happens? If they are below the wavelength of a light, so they go to the Rayleigh scattering regime. So the Rayleigh scattering is very weak compared to the Mie scattering. So almost like the couple of orders magnitude weak. So Mie scattering is very strong. So all I think you can see that why there is a nice physics explanation saying that whatever is the clouds you see or the brightness you see is Mie scattering, and whereas the sky blueness is Rayleigh scattering. So where this that blueness is through a molecular, through the atmospheric molecules, which are very small compared to the wavelength of the light, right? Anyway, so this should be large enough so that you get a Mie scattering, not go into the Rayleigh regime. It will not be able to capture in the camera. So you need like the other instruments like uh, this, and then the particles need, if the refractive index is different, then it will be transparent. You will not be able to see anything there. So and then seeding density. Seeding density is number of particles you put. It should not be too high or it should not be too low. Too low, then you will not have enough pairs. If it is too high, you can't, again there will be though it is, you need to have some pattern, otherwise it will just look like a single one. And typically used ones are like for air, people do use smoke or fog or oil drops. So which we'll be demonstrating, like you can use a oil drop. All is, you need to put a small nozzle into the pool of oil, right, and inject the gas. This gas will come and take some oil drops out. For water, if somebody is doing in a combustion, if you want to measure the velocities in a flame, you can't put any of these liquid drops, they will burn, right? You need to have very fine particles which withstand that high temperature. So usually use a titanium particles. And water, it is, so you can have slightly heavier particles. If somebody is doing water flow inside the water, they can use gas bubbles, gas bubbles, glass microspheres, polystyrene. So right, so yeah, so this I think these are some basics about PIV. I'll stop here. All right.